Just as a reminder, I put some notation from last time on the blackboard. So we were working over a non-Archimedean field of Laurent series over a field small k of characteristic 0. And so our non-Archimedean field is denoted by capital K. And then last time I explained how to analytify algebraic varieties over capital K. And so in today's talk, we will always assume that our variety X is connected smooth and proper over K. So this was a convention that we already introduced last time in order to define monomial points. So the first thing I want to explain today, to fulfill a promise that I made last time, is how we can use these monomial points to understand the topological structure of the Berkovich analytification of X, and in particular its homotopy type. And so for this, we introduced the following definition. So suppose that curly X is a DLT model for X. And again, if you don't feel entirely comfortable with DLT models at this point, you can just think of it as a strict normal crossings model without too much loss of generality. And I write the special fiber as a sum of Ni EI, where the EI are the prime components and the Ni's are their multiplicities. And then we can define the so-called Berkovich skeleton. Of curly X. So this is denoted by square of curly X. And by definition, it's just the set of all monomial points on the Berkovich analytification with respect to curly X. So by construction, this is a subspace of what we called the space of birational points last time. So the space of all the real valuations on the function field of X extending the discrete valuation on the base field K. And so I explained last time, I didn't give you a precise definition of monomial point, but I explained what are the data that we need to construct these monomial points. So we needed to fix a DLT model, a stratum in the special fiber, and then continuous parameters that somehow interpolated between divisorial points attached to different components of the special fiber. Yeah, and so here we consider the monomial points which are defined on our fixed DLT model curly X, where we allow the stratum C and the parameters alpha to vary as we like.
Johannes, are you writing Xn as a subset of Xp?
No, this set is a subset of Xp, the skeleton. Sorry. Yeah. By definition, monomial points are always supported on the generic point of X. So these are evaluations on the function field. And so what is so nice about this skeleton is that we can explicitly describe its topological structure. And so we can compare it in particular to the dual intersection complex. Of the special fiber. So this is a pretty standard notion in the case of strict normal crossings models, when the special fiber is a strict normal crossings divisor. But the definition extends immediately to the DLT case. So this is a finite simplicial complex. Such that, well, the vertices correspond canonically to the irreducible components of the special fiber. So these are the EIs in our notation. And then we have to decide how these vertices are glued together inside the dual intersection complex. And for this, we use the geometry of the strata of the special fiber of higher codimensions. So there is an inclusion reversing bijection. between simplices of dimension d and strata of the special fiber of codimension d. And so generalizing the d equal to 0 case, which is just correspondence between vertices and irreducible components. So let me make a picture, if this is the first time you see this notion. So we can look at a situation where the special fiber is just a curve consisting of 3 components, E1, E2, E3, that intersect as in the picture. And so in this case, the dual intersection complex is usually called the dual graph. So I take a vertex for each of the irreducible components, V1, V2, V3. And then, well, I need to decide how I'm going to join these vertices by edges. So E1 and E2 intersect in 2 strata, the 2 connected components of their intersection. So this means that I have 2 edges joining V1 and V2. And then E3 intersects E2, but not E1. And the intersection is just 1 stratum, one intersection point. So I have 1 edge going from V2 to V3. And so this is my dual intersection complex in this case. And there's a natural generalization of this picture to arbitrary dimension. So now we can consider the following map, phi, which goes from the Berkovich skeleton to the dual intersection complex. And this map is constructed by observing that the data you need in order to define a point of the skeleton, a monomial valuation on curly x, are precisely the data you need in order to choose a point on the dual intersection complex. So more precisely, if I have a monomial point associated with curly x, a stratum C, so E1 to ER are the irreducible components of the special fiber which pass through C. And then I have this tuple alpha of continuous parameters. Then this point is sent to the point on the face corresponding to the stratum C. With barycentric coordinates alpha 1 and 1 dot alpha r and r.
So, what were your assumptions on the special fiber?
Just DLT. My model curly x is DLT.
And you claim that it's always a simplifier complex?
It's it's the topological realization of a finite simplicial set. So for me, simplicial complex, I allow multiple faces spanned by the same set of vertices, like in the example that I gave. Yeah. Why does this construction make sense? The face, by definition of the dual intersection complex, the face corresponding to my stratum C has the property that it is spanned by the vertices corresponding to the components E1 to ER. So once I've chosen an ordering on these components, E1 to ER, I have an ordering on the vertices of C, and thus I can speak of about a tuple of barycentric coordinates of a point in my face. And then we have always chosen the parameters alpha in such a way that alpha 1 and 1 to alpha n, alpha r and r sum up to 1. So this means that this is a tuple of barycentric coordinates, which I can use to identify a point on my face. And that's exactly the image of my monomial point under the map phi. the map phi is homeomorphism. So this is not difficult to see, well, except that I didn't tell you what is the definition of monomial point. But once you use the definition, it's easy to check. So from the description that I gave, I think you can believe that this is a bijection, just because we use the same set of data to define points on the left and points on the right. So it's going to be continuous with respect to the Berkovich topology on the skeleton, essentially by definition of the Berkovich topology. Because my monomial points move continuously in families. Since the source is compact and the target is Hausdorff, I know that, well, I guess I didn't actually prove that the source is compact. Well, let me do it the other way around. So you can define, once you know it's a bijection, you can take its inverse. You check continuity there. This thing is compact, this thing is Hausdorff, so you know it's homeomorphism, and then you're done. Yeah, so this is an extremely useful proposition, but which is not difficult to prove. And then we know more. Moreover, there is canonical retraction rho curly x, which goes from the Berkovich identification of x to the skeleton. And somehow you should think about this as the best approximation by a point that is monomial with respect to curly x. Yeah, so if you take any point on the Berkovich identification, you think of it as a real valuation that lives on a residue field of one of your schematic points of x. And then you construct a monomial point in such a way that the center of your two valuations lie in exactly the same stratum. And such that if you take the irreducible components of the special fiber passing through this stratum, you take local equations for these components, and you take the absolute values of these equations at the point and at its image under this retraction map, then these are the same. And so somehow it's the optimal approximation of a Berkovich point by a monomial point on curly x. And then there are two important results which tell us that skeleta control the topology of the Berkovich identification X-an. So again, the first result is basically a restatement of a classical result in theory of Riemann-Zariski spaces. So let me state it as a proposition. The retractions rho x define a continuous map from the Berkovich identification 2. So now instead of taking one DLT or SNC model, curly x, I consider the whole projective system of such models. And instead of considering one skeleton, I take the whole projective system of these skeletons. And so I can take its limit. And this gives me a continuous map from the Berkovich space to the projective limit of these skeleta. So where curly x runs over the set of DLT models or SNC models, that doesn't matter. And so the proposition tells us that this is a homeomorphism. Yeah, so this is an extremely useful result because it tells us that points in the Berkovich space are completely characterized by their projections to the skeleta of all DLT models or the skeleta of all strict normal crossings models. And so I said this is basically a consequence of a classical result in Zariski-Riemann spaces. So in general, if we have a valuation, say, living on the function field of X, then we know that this valuation is completely characterized if we know its center on the special fiber of all the proper models of X. But in fact, knowing the center on all the proper models is the same thing as knowing the projection to the skeleton for all SNC models or all DLT models. So this is a little lemma that you can easily work out by yourself. But so this tells us that knowing a Berkovich point is the same thing as knowing all of its approximations on skeleta of SNC models. So on the other end, this result has the obvious downside that in order to understand the topology of Xn, we need to understand the skeleta of all strict normal crossings models at once. And there's a much deeper result, which is a variation on results by Berkovich and Tillier. Which says that working on one strict normal crossings model is enough if you're only interested in the homotopy type of the Berkovich space. So let curly X be an SNC model of X. Then the map rho curly X. So this was a retraction map from the Berkovich identification to the skeleton. Extends to a strong deformation retraction. Of the Berkovich identification onto the skeleton. Yeah, and again, we've just argued that the skeleton is homeomorphic to the dual intersection complex of the special fiber. So this tells you that if you understand the geometry of one strict normal crossings model, then you completely understand the homotopy type of the Berkovich identification Xn. And as a, yeah?
Excuse me, do you need the normal crossings or?
Eventually not, but the version that was proven by Berkovich-Tillier only works for strict normal crossings models. So we will discuss extensions to DLT models a bit later. So one interesting corollary of this statement is the fact that the homotopy type of this dual intersection complex turns out to be independent of the choice of your SNC model curly X, which is not at all obvious at first. Just because it's homotopy equivalent to something which doesn't depend on anything except on X itself, namely the Berkovich identification. So that's a nice bonus. And so in the way that Berkovich and Tillier proved this result, it's really crucial that we work with strict normal crossings models rather than more generally DLT models, because they use the toroidal structure of the special fiber. So working on étale charts, they reduced essentially to a toric situation. And then you can use the torus action to push all the points of the Berkovich space towards points of the skeleton. So it's a beautiful result and extremely useful to understand the properties of these Berkovich identifications. So with these results at our disposal, I can finally give you an example. I can make a picture of a Berkovich space. And in fact, whenever you open an introductory text to Berkovich geometry, this is a picture that you will see appearing somewhere. We are going to discuss the identification of so-called Tate curves. So what are Tate curves? So these are elliptic curves, E. Which have split multiplicative reduction. So another way of phrasing that property is saying that if we consider its minimal SNC model, then the special fiber looks like a cycle of projective lines. Okay, so one thing I can immediately see is well, the homotopy type of the Berkovich analytification, because I know that Ian is a homotopy equivalent to the skeleton of my SNC model, which is homeomorphic to the dual intersection complex of the special fiber, which is just a circle. So analytifications of Tate curves are homotopy equivalent to S1. And moreover, we have our retraction map rho, which is associated with our particular choice of SNC model, which goes to the skeleton of our SNC model. And so we've seen that this is a homotopy equivalence. So this is the easiest example of a non-archimedean SYZ fibration. Because, well, saying that our elliptic curve is a Tate curve implies in particular that it's maximally degenerate in the sense that I defined in the introduction. So the monodromy acting on the degree 1 cohomology of our elliptic curve will have a Jordan block of size 2. And so SYZ conjecture predicts that on our elliptic curve there should be a structure of a fibration over an S1. And that's exactly given by this canonical retraction map rho. At least in the world of Berkovich spaces. But we can go a bit further. So instead of just determining the homotopy type, we can try to make a picture of the whole Berkovich space using the first proposition on the right. So for this, we have to understand what happens to our skeleton if we move up in a tower of strict normal crossings models. Now, in the case of relative dimension 1, the only thing we can do to produce new strict normal crossings models is blowing up points. So we just need to investigate what happens to the skeleton if we blow up a point in a special fiber. And then there are essentially two things that can occur. So the first type of blow-up that we can consider is we can blow up an intersection point of two components in a special fiber, which gives us a new copy of P1 of multiplicity 2. And then the effect on the skeleton, so let's say this is a special fiber of our new SNC model curly E prime. So the skeleton of E prime looks exactly the same as the skeleton we had before. So the only thing that changed is that we have a new vertex in the simplicial structure, which will lie in this case nicely in the middle of the edge that we had before. So blowing up intersection points in a special fiber just corresponds to subdividing edges. But there's another type of operation that we can consider. So we can blow up at a point which is not an intersection point of components in a special fiber. Sorry, I put my picture upside down. So this means that I get a new component like this. And then my skeleton will actually grow. Namely, I have a new edge which will be attached to the vertex corresponding to the irreducible component that contains the point that we have blown up to create a new SNC model, E double prime. Yeah, so the two operations that we can perform are either subdividing edges or attaching new edges to vertices. And then by passing to the projective limit,
the number of curves doesn't include on different prime K and the skeleton.
sorry, I didn't understand the question.
The number of curves on D prime K and the skeleton doesn't match.
Wait, I have 6 components here, and I have 6 vertices here. It's a dual intersection complex, not the intersection complex. I don't know if that was the... So passing to the projective limit, we get the following picture for the identification of the elliptic curve E. So in the center, we have the skeleton of our minimal SNC model. And then out of the skeleton, we have an infinite number of branches that shoot off like this. So I'm clearly not going to draw an infinite number of branches. So what happens is that we get some kind of fractal tree structure of this type. And so it's interesting to try to classify the points that appear in this picture. So there are 4 types of points that occur in the Berkovich classification. So the first possibility is that by following an edge all the way to infinity, we actually end up at a closed point of E. So this is what I tried to explain last time, that to a certain extent, the closed points of our variety are irrelevant to understand the topology, or at least the homotopy type of the Berkovich identification. Because we have to picture the closed points of our elliptic curve as forming some kind of cloud that lies at the boundary of our Berkovich space. So then there's a second type of point, which is a branch point of our tree. So the branch points, maybe I think I have enough colors to do them all. That's right. So these never live in a skeleton because they're not birational points, but they are approached by monomial points. So the branch points in my picture are precisely the divisorial points. Because, well, from this construction, it's clear that our tree can only branch at a point which is a vertex for some simplicial structure coming from a strict normal crossings model. So a point which corresponds to a divisorial valuation attached to an irreducible component in a special fiber. And then we have the intermediate points. So these are the non-divisorial monomial points. Yeah, and so on this picture, you can see that the branch points, so the divisorial points, they will lie densely inside all Berkovich space, but they're totally disconnected. And so the monomial points have exactly the merit that they interpolate between these divisorial points. And so you can, sorry?
So for the closed point of E, what monomial variation do you approximate?
Oh, so you can just, you specialize it to the special fiber. You blow up the specialization points, and you repeat this process infinitely many times. And then you create a sequence of points that will converge towards your closed point in the Berkovich space.
Is it easy to see why it converges?
No, and actually in higher dimension it becomes a bit more tricky. This process will not necessarily converge to the point that you started with. But for curves, you can work this out. So life would be very pleasant if these were the only points that appeared in a picture. But in fact, there's a different type of phenomenon that can occur. So let's see if I can find the ugliest color in the box. That must be this one. So if you start following a branch shooting off from the skeleton, it can happen that your branch will die off without ever reaching a closed point of the elliptic curve. And so these are the so-called type 4 points. And so algebraically, they correspond to the fact that if you consider completion of the algebraic closure of your field capital K, then in general, this valued field can have some weird extensions, which are called immediate extensions, which have the property that under this extension, the residue field stays the same and the value group stays the same. But nevertheless, your extension will be non-trivial. And so these extensions also give rise to Berkovich points, which are called type 4 just because we don't have any better name for them. And so they're very important in the sense that they are necessary in order to compactify the Berkovich space, but they don't correspond to anything very precise in birational geometry, so they just occur as limits of other points. And so on this picture, you can also see the strong deformation retraction to the skeleton at work. So what it's going to do is just, it will start at the outside of your branches, and it will suck in all the branches into the skeleton. And that's your strong deformation retraction of the Berkovich identification onto the skeleton. So that's, I think, a very convenient picture to demonstrate that non-Archimedean geometry has something to do with the conjectural properties of the SYZ fibration. Wow. Oh, no. The base of the SYZ fibration is just a circle, S1. So the fibers will be these branches sticking out of the skeleton in my picture. And if, in fact, in this picture, if you use a little bit more Berkovich technology, so if you use sheaves of analytic functions, which I haven't introduced, you will see that in a very reasonable sense, the fibers of this retraction map rho are tori, just in the sense of non-Archimedean analytic geometry. So again, they satisfy the properties that are expected from the SYZ conjecture. No, not that I know of. That's right. I'm sorry?
How can you think of a tree as a toast?
Yeah, so if you compute analytically the set of points in a Berkovich space that are, so let's see how I can explain. So if you have two components intersecting in a point, and you want to know. So you have corresponding edge, which is part of your skeleton. So you can parameterize it by means of your barycentric coordinates. So suppose that I have a point which I call R here, where R is some real number. Then in the sense of non-Archimedean analytic geometry, the fiber can be identified with an analytic subspace of the Berkovich analytification, which is defined. So the fiber is a subspace of the analytification of a one-dimensional algebraic torus, defined by an equation of the form absolute value of t is equal to r, where t is the coordinate on the torus. And this is a torus in the sense of non-Archimedean geometry. So this you can figure out once you use the precise definition of this retraction map, which again I have omitted for reasons of time. But now, of course, the situation we've been looking at here is quite special in the sense that we had a minimal SNC model. Well, as you all know, the situation gets less nice if we move to higher dimensions. So in higher dimensions, we have no minimal SNC model in general. And the question is, can we still define a canonical skeleton plus a retraction map rho? So that again, we have a picture that looks like a non-Archimedean version of the SYZ fibration. And so here, Kontsevich and Soibelman, they suggested the following construction. So this will be part 3 of my talk. So I still assume that X is smooth and proper and connected over K. So the idea is that in the first instance, we're not going to try to construct some kind of canonical SNC model, which is not going to exist anyway. But we will use some additional data on X in order to identify essential pieces of the skeleton of any possible SNC model. And so the idea is that if we just fix an SNC model at random, then some of the faces of the skeleton will be there because we made an unfortunate choice of SNC model. But some of the faces will be there because there are very good geometric reasons why they should be there in the first place. And so the additional piece of data that we're going to use in order to find these essential faces of the skeleton is a pluricanonical form. So let omega be a non-zero M-canonical form on X, where M is a positive integer. So this means a non-zero global section of the M-fold tensor product of the canonical line bundle on X. No. It may vanish. At a later point, we're going to specialize to the case where we work with Calabi-Yau, and we will take a volume form. But construction is much more general. So what can we do? Well, whenever we fix a regular model of X over R, then we know that we can extend this line bundle to the model in a canonical way. In fact, in different or in several canonical ways. So the extension I'm going to pick is the M-fold tensor product of the relative canonical line bundle of my model, which exists because of the regularity assumption. But for technical reasons, we will consider its logarithmic version, which means that we twist by the reduced special fiber. And so omega is a global section of this guy. So it's going to be a rational section of this guy. And so we can take the divisor, so the Cartier divisor, associated to omega. I'm sorry?
Why does the regular model exist? Oh, you're in characteristic.
I'm in characteristic 0, yes. Otherwise, this would be an assumption in dimension at least 3. That's right.
Curly X is the canonical model, or what?
No, curly X at this point is just any regular model.
Oh, it's the regular.
Yeah.
Sorry.
And then we can make the following definition. So suppose that E is an irreducible component of the special fiber. Of multiplicity n. And suppose that mu is the multiplicity of E in the divisor which I've just associated with omega. And x is the divisorial point in xn associated with curly x and E. Okay, so the rescaled divisorial valuation induced by E. Then we can define the weight of omega at this point x. As the quotient mu divided by n. And it should be obvious from the definition that this only depends on the divisorial valuation x and not on the choice of model. And now Kontsevich and Soibelman introduced the following definition. Sorry, the weight of omega at x. Omega is a rational section. I've just assumed that it's a... That's right, that's right. So omega is a regular section of the pluricanonical line bundle on the generic fiber, but it may have poles along the special fiber. So Kontsevich and Soibelman have attached a skeleton not only to the variety x, but which will also depend on our choice of pluricanonical form omega. And so the definition is the following. So we take the set of divisorial points in xn where the weight is minimal. And then we take its closure in the Berkovich space xn. So these are divisorial points which are special in the sense that they minimize the weight of omega. And well, Kontsevich and Soibelman, they were essentially interested in the case where x is Calabi-Yau. So in that case, there's basically only one choice for omega to make, namely volume form. But if you want to generalize their construction to a more general situation, you can define the essential skeleton of x just by taking the union over all possible omega. And the idea is that this guy should be some kind of canonical skeleton living inside the Berkovich space. Yeah, so, well, first observation is, of course, that it only depends on x. And a second observation is that it's only interesting if x has enough pluricanonical forms. Yeah, because, well, to give an extreme example, if x is rational, then we're taking a union over of an empty family, and the essential skeleton will also be empty. So this essential skeleton has the advantage of being completely canonical, but from the definition, it's very hard to visualize what will be its geometric properties. In order to achieve this, one can extend the definition of the weight from divisorial points to arbitrary points in the Berkovich space. And so then we will see that we can define this Kontsevich-Soibelman skeleton as the locus of minimal values of a function which is defined on a nice topological space, and the function itself will have very nice properties as well. And this gives us some control over the shape of the Kontsevich-Soibelman skeleton, and there's also of the essential skeleton. So let me define this weight function by means of a theorem. So it's really a combination of results that appeared in my work with Mircea and then later with Chenyang. So let omega be a non-zero canonical form on X. Then there exists a unique smallest function which we call the weight function. And which depends on both x and omega. So it's defined on the whole Berkovich space Xn. It takes values in R union plus infinity. For instance, at closed points of x, the value will automatically be plus infinity. So it's interesting mainly on the space of birational points. With the following properties. So it's not going to be continuous on the entire Berkovich space, but it's going to be lower semi-continuous. But what is important for us is that it has very good properties with respect to skeleta of DLT models. So if curly X is any DLT model of X, and X is a Berkovich point that lives on the skeleton of our DLT model, so it's going to be monomial with respect to this DLT model. Then we can explicitly compute the weight as follows. So the weight at X will be the valuation associated to X. So we've seen that we can identify birational points with real valuations on the function field. Of F, where F is a local equation for the divisor of omega at the center of my valuation Vx. Yeah, so here I'm slightly abusing notation because I've only defined this divisor of omega in the case of regular models. But since X is a monomial point, its center will automatically be a generic point of a stratum of the special fiber. And by definition of DLT models, at such a generic point, my model is actually SNC, and in particular regular. So it makes sense to speak about this relative canonical line bundle and the divisor associated with omega. So this implies that the weight function is continuous and piecewise affine on the skeleton. It will be concave on every face. and it will be affine on a face. If and only if the corresponding stratum does not lie in the closure of the locus of zeros of omega on the generic fiber. Yeah, so what happens is that if we look at the divisor of omega, well, its support will contain some components of the special fiber, but it may also contain some horizontal components which come from zeros of omega on the generic fiber. And so my function will bump, so be non-affine, but strictly concave on a face, even only if the corresponding stratum lies in the horizontal part of this divisor. So the bump is caused by zeros of omega on the generic fiber. And then I need 1 more minute to write down the last property to finish the theorem. If again curly X is any DLT model, and X is a point on the Berkovich analytification, then the weight function, or the weight at X, will be at least the weight at its projection to the skeleton. And equality holds even only if our point X lies already on the skeleton. So this means that if I start moving away from the skeleton of a DLT model, then the weight function will always be strictly increasing. So the first property is essentially a translation of the property that the pair consisting of curly X and the reduced special fiber is log-canonical. And the second property is a translation of the fact that every log-canonical center meets the strict normal crossings locus. So this really comes from the fact that we work with DLT models in a serious way. And so how does this help us to understand the geometry of the essential skeleton? It tells us that, well, just by this continuity property on skeleta, we know that the Kontsevich and Soibelman skeleton is the locus where the weight function reaches its minimal value. Yeah, so there's no longer any need to take closures. And the essential skeleton is a union of faces of the skeleton of any DLT model. Yeah, because by the last property, we know that locus of minimal values lies entirely inside the skeleton of our DLT model. If we move away from the skeleton, the weight function will go up. And then these properties tell us that on the skeleton, the locus of minimal values is always going to be a union of faces. So this gives us some control on the shape of the essential skeleton. It's going to be a finite simplicial complex. Next time, we're going to use the MMP in order to get an even stronger grip on the precise shape of this guy. And so a good example to keep in mind is the example of the Tate elliptic curve. So then the weight function attached to any volume form will be constant on the circle in the middle. This will be the essential skeleton in that case. And then it will be increasing constantly with slope 1 if you move away along the branches towards infinity. So that's again the easiest example of this construction. I'm sorry for going over time. I'll stop here for today.
Any question for the speaker? Oh, just a second. So are the faces of SKX exactly those
those that appear on every DLT model?
That's right, but that will be a consequence of a result that we're going to discuss tomorrow. So what we're going to show is that the essential skeleton is just a dual intersection complex of a minimal DLT model. So if you assume that the canonical line bundle on the variety X itself is semi-ample, you have minimal DLT model, and then minimality will guarantee that the Berkovich skeleton of minimal DLT model is exactly the essential skeleton.
Other questions? If not, then thanks to the speaker again.